Today we're going to take a look at section 4.3, which is greatest common divisors and least common multiples. My goal will be for us to cover greatest common divisors in class today, and then I'll post the video for least common multiples from last semester for you guys to watch on Friday, okay? By definition first, what are we talking about when we're talking about greatest common divisors or greatest common factors? We're looking at the greatest whole number that divides all numbers in your set. So it's kind of tricky, because the word greatest makes it sound like you're talking about big things. But the word divisor means it has to divide the number you're working with. So these are not large numbers. These numbers are smaller than what you've already started working with. They're just the biggest number that will divide them. I've used this phrase multiple times now, relatively prime. Relatively prime numbers are two numbers who have no common factors but one. Everything has one. You can also talk about them having nothing in common. I think I've used that phrase before. There's another phrase once we get into least common multiples that can be used to redefine this in terms of multiples, and we'll talk about that later, okay? But relatively prime, numbers that have no common factors other than one. So what we're going to look at then is we're going to look at several models for finding greatest common divisor. You probably haven't seen all these models. That's fine. Or methods rather. The first one is called the intersection of sets method. This method works really well when you're dealing with smaller numbers and numbers that just don't have a lot of divisors. If the numbers have a lot of divisors, this becomes, I don't want to say messy, but it just becomes a lot of work. It becomes detailed and just kind of an overload of stuff. If you're thinking about like where does this material kind of end up getting taught in schools? This is 4th grade stuff. I was chatting with I think it was your group last time you were here. And interestingly enough, one of my children who's in 4th grade brought homework on greatest common divisors. So yep, it's 4th grade, at least right now in terms of curriculum standards. So an intersection of sets method means that you list all the divisors of each factor, of each value. You list everything out, and then you just look for the one that's the biggest one in the list. Okay? So we're going to do an example with the numbers 12 and 15, and as you see, I did choose small numbers. This method works really well when the numbers are small. And what we're going to do is we're going to make a list of all of the divisors, not primes, but all the divisors of 12. So I start with 1. And if you want to, you can make them in duplicate forms, right? It's 1 and 12. We've done this before. What's the big number after 1 that would be divide 12? 2, and they come in pairs, so 2 and 6, and then what? 3 and 4. So my list is kind of doing like this, right? In terms of the numbers from smallest to greatest. But those are the numbers that divide 12. Then we're going to do the same thing for 15. Always start with 1, so 1 and 15. What's next? 3 and 5. And that's actually it. So what number is in both lists, and it's the biggest number in both lists? 3. Which isn't very big. Agreed? It's just not. You know, greatest common divisors are typically small values. Notation, how do we write this? Well, we're looking at a greatest common divisor, so GCD. And to be specific, just because I'm going to use this here notation next class period, the GCD of 12 and 15, so I've got the 12 and the 15 in there, is 3. That's the answer. Okay, so if you think about some numbers that have like lots and lots of divisors, like I think about the number 64. 64 has a lot of divisors. This could be very tedious. It could. You have a long list. But if the lists are very short, this is very quick and it's easy to work with. Second method, prime factorization. So the prime factorization method is the one that I remember learning in school. This is the only one I remember learning. And what I did, or what we do with this method, is that you construct the prime factorization of each number. So you break it down, each of the numbers, into its primes. You choose all the prime numbers that they have in common with the smallest exponent on either number. And then you multiply that out. When the numbers are small, like 12 and 15 on the previous slide, this is a lot of work because it's overkill. You do a whole lot of work with a very simple answer you're looking for. It's overkill. But when the numbers are larger, it works much more efficiently than the listing them all out, like in the previous method. So we're going to find the greatest common divisor with some large numbers, because that's what this is useful for. So I need to do the prime factorization. If you want to do factor trees, that's fantastic. I'm going to do my division ladder. So here's my 400. And I start with the smallest prime, 2. 400 divides by 2 to give me 200. Then what? 2 again to give me 100. And then what? 2 again to give me 50. And then 2. 25, 5, and 5. Now, the prime factorization then here is nicely put over here. I have 2's and I have 5's. How many 2's do I have? 4 of them, so that's 2 to the 4th. And how many 5's do I have? 2. So the prime factorization for the number 400 is 2 to the 4th times 5 squared. Next one, 360. Well, that's another 2. What's 360 divided by 2? 180. 180 divided by 2. 90 divided by 2. 45. Doesn't divide by 2 anymore. Does it divide by 3? Yes. How did you know? 4 plus 5 is 9, and 9 divides by 3. Good job. 45 divided by 3 then is 15. Does 15 divide by 3? Again, yep, to give me 5. So I have 2's, 3's, and a 5. How many 2's? 3. How many 3's? 2. And how many 5's? Just 1. And if it helps you, write a 5 to the 1 there, write a 5 to the 1. Whatever helps you to see it best. Okay, so we've done step 1. Step 1 is to write out prime factorizations. Step 2 is to choose from my list of prime factorizations what bases, what factors do they have in common? What factors do they have in common? They have a 2. Hang on the squaring and things, but they have a 2 and what else? And a 5. Okay, so that's step 3, or 2. Step 3 is to identify what the powers are. So what we do is we use the smallest power for each one of those. So this is 2 to the 4th, and this is 2 to the 3rd. So what is the smallest number of 2's they have in common? I shouldn't say it that way. What is the smallest exponent on the 2's? The 3, all right? They have 3 3's in common. One of them actually has 4 3's, but there are 3 3's in common. How about 5's? Just 1, because one of them has 2 and one of them has 1. And then your last step is to multiply that out. What's 2 cubed? 8. And 8 times 5 is 40. Okay? The next method's my favorite. This works fine. I can do this and all of that, but even it is kind of overkill. For example, on the right-hand side, that number 360 on this example, there was really never any need to divide by 3. There really wasn't, because 3 wasn't in the other list at all. But if I'm trying to find the prime factorizations, that's part of the process, right? Okay, so division by primes eliminates some of the unnecessary steps. What we do is we write the numbers in a row. We look for a factor common to both of them, and we divide by that prime factor. And then we repeat. We keep dividing each of the factors by each of the results by a prime factor that's in common. And then everything that we divided by, multiplied back out together, is our GCD. So I'm going to do, I know this says 410 divided by 360, but I'd really like for us to try to do it with the same numbers we just did, because I'd like for you to see where it is that we actually save some time in the process. So let's try it with 400 and 360. Okay, so what I do is I write the numbers on the same line. That's kind of what it said. And I'm going to do that same algorithm that I did before. And I'm looking for the smallest prime number that they both divide by. So what is the smallest prime that they both divide by? It's 2. And I get 200 and I get 180. And I repeat, 200, 180. Do either of those two numbers divide by another common prime? 2 again, to give me 190. Do they divide by another common prime factor? 2. And that gives me 50 and 45. So at this point, you can look at either number you'd like, but you're still looking for prime factors. Do both of them divide by 2? No. So we're going to move up the chain of primes. Do both of them divide by 3? No. Do both of them divide by 5? Yes. So we move on into the 5s. What's 50 divided by 5? 10. What's 45 divided by 5? 9. Once I get to 10 and 9, those do not have anything in common, and I'm done. And the answer is all these numbers that I divided by. So my GCD of 400 and 360 is 2 times 2 times 2 times 5, which is 40. Do you see that I saved myself time? There's division I didn't have to do. Brooke. Yeah, it's a good question. The answer is technically that it will work without doing it with primes. However, the name of the method is division by primes, so that's what their intent is behind the method. So is it really necessary that they be prime numbers? And the real answer is no. But for the sake of the way that this is structured, we're going to do it with primes. Yeah. All right, there's one more method, and this one is probably used the least, but I want you to be aware of it. Any questions on this one before we go to the last one? Okay. This is called the Euclidean Algorithm. The Euclidean algorithm says to take the larger number divided by the smaller one, and then whatever you get as a divisor, you divide it by the remainder. And you keep doing that process over and over again until you get a remainder of 0. This is one of those things, kind of like my divisibility rule by 11. It's weirder to write to actually do. The doing of it's really not that difficult. Writing it down is super weird. All right, you ready to try one? Okay, so we're going to use the numbers 72 and 126. And I need you to divide the larger number by the smaller one. So 126 divided by 72. How many times will 72 go into 126? 1 time. So then I will subtract 76. What is 126 minus 76? Not 76, 72, sorry. That's not right. 72. What's my remainder? 54. Okay, so here's what I do next. I use the divisor, and I use the number that's the remainder, and I do it again. The divisor is now underneath 72, and the remainder is now on the outside 54. How many times will 54 go into 72? Just once. The answer is not always 1 on top, by the way. It just has been so far. So I subtract 54. What is 72 minus 54? 18. And I do it again with the 18 and the 20 and the 54. So 18 is going to divide 54. How many times will 18 go into 54? It's 3. What's 3 times 18? 54. So when I subtract at this point, I end up getting a remainder of 0. And eventually you will get a remainder of 0. Okay? You will eventually get a remainder of 0. And at the point when you do, the last number that you divide it by is your GCD. 18, sorry. My GCD is 18. When I get a remainder of 0, this is how I know to stop. You don't see this one used very much. Not going to lie, you may never teach this, and that's okay. However, it is another way of doing the division, and it's not anything complicated. It's division and subtraction involved in the division, right? Alrighty.